red black tree. So what is a red black tree? Red black tree is a special type of data structure. It is a self-balancing binary search tree. You already know about binary search tree. Now it satisfies all the properties of the binary search tree, but besides all that properties, it has some specified properties of our own. These four properties must be satisfied if a binary search tree is to be considered as a red black tree. The four properties are listed below and will be explained thoroughly in the further slides. The first condition for a red black tree is that all the nodes of it must have color either red or black. There are no possible colors for nodes other than red or black. We can see over here that the node 7 has color black. Likewise 8, 3, 10 and 22 have color black, while 8, 11, 12, 26 and 18 have color red. Okay, yeah, another concept that comes over here is the concept of nil node. Like in binary search tree, there the nodes which we had only had key values in them and no null nodes were present, but in red black tree there are special nodes known as nil nodes which must always be colored in black and they do not store any value, but we consider that nil nodes as leaf nodes. So an important property of red black tree is that the root and leaves, which are nil nodes, all the root and nil nodes must be black in color, and this property cannot be violated. Another important property of a red black tree is that if a node is red, then its parent must always be black. That means that a red child must always have a black parent, but the converse is not true for black child. A black child can either have a red parent or a black parent. Another and most important property of a red black tree is that all the paths from any node X to any other nil node must have the same number of black nodes. Like considering all the paths from 7 to any other nil node, be it this nil node or this nil node, the number of black nodes must be same if the tree is to be a red black tree. Like considering this particular path, the number of black nodes from 7 to this nil node is 1 and 2. So two black nodes. Likewise, considering this particular path, the number of black nodes from 7 to this particular nil node are also 2. Likewise, if we consider path from any node to all other nil nodes that lie in the subtree of that particular node, the number of black nodes which lie in the path to all other nil nodes must be same. Only then the properties of a red black tree will be satisfied and the tree binary search tree can be called as a red black tree. Now another notation has been used over here which is called black height. The black height of any node in the red black tree is the number of black nodes which lie in the path from that particular node to any of the nil nodes. So for 7 the black height is 2 because from 7 to any other nil node the number of black nodes lying in the path is 1 and 2, and this will be same for all the paths from that particular node to nil node, and thus black height of that particular node will be 2. Now we'll look at some of the examples of BSTs which are not red black trees and why they are not red black trees. This particular BST is not a red black tree because it has a red child and a red parent, which is not possible and violates the rule 3. And all these remaining 3 B, C and D BSTs violate the fourth condition, which states that the path from node to any node to all other nil nodes must contain same number of black nodes, which is violated over here, as here it has only one black node while here it has 2 black nodes on the path. So this condition is not satisfied in B, C and D, and thus all these 3 are also not red black trees, violating the condition 4. Now let us discuss about the height of a red black tree. There is a theorem that states that a red black tree with n keys has heights h less than equal to 2 of log n plus 1, where n is the number of keys that are present in the red black tree. Now we'll prove this result theoretically, but first we need to consider an intuition. The intuition is that we'll merge all the red nodes in their black parent. So we can see over here all these red nodes are eventually merged over here in the black parent, considering leading to the formation of a 2, 3, 4 tree. The new height of the 2, 3, 4 tree thus formed will label the new height as h dash. So now we have to understand the fact that h dash will always be greater than equal to h by 2 because at most half of the leaves on any path will be red. Okay, so now if we consider the basics of a tree, then we know that the number of leaves in each tree having n keys will be n plus 1, and since this is the 2, 3, 4 tree, the n plus 1 leaves shall follow the property n plus 1 greater than equal to 2 to the power h dash less than equal to 4 to the power h dash. So solving this equation with the help of logarithm and combining it with this particular equation leads us to the final result h less than equal to 2 into log n plus 1, which is the theorem for the height of the red black tree. The query operations such as search, min, max, successor and predecessor all run in O log n time on a red black tree. The modifying operations that are present on a red black tree are insert and delete operations. Besides this, there are also color changing operations and restructuring the links operation, which we'll understand in further discussion. Now we'll understand different possible cases of insertion in a red black tree and with the help of various examples. The first step of insertion is that we have to perform a standard BST insertion and make the color of newly inserted node as red. So the first case that comes is that if X is the root, then we'll simply change the color of X and black, and this will increase the black height of the tree by 1. Okay, then the next case is that if X's parent is black, there is no need to change anything because this is a red black pair and it does not violate the conditions of a red black tree. Earlier we considered the parent of X was black in color, so it formed a red-black pair, but now we considered that X's parent is not black and thus it is red, and so it will violate the conditions of two red cannot being together in a same red-black tree. So now the first condition is that if X's uncle is red. Okay, so what is uncle? So this is the parent of X, then grandparent is the G is the grandparent of X, and the other sibling other than parent will be the uncle of X. So U over here is the uncle of X. Okay, P is the parent of X and G is the grandparent of X. So if X's uncle is red, then we'll simply change the color of parent and uncle to black, and we'll change the color of grandparent to red, and then we'll repeat steps 2 and 3 for the grandparent unless we reach the root or unless we are able to see a stable red-black tree. Earlier we saw that the uncle of X was red, but now what if the uncle of X is black? Then if the uncle of X is black, there are 4 possible configurations further for X, X's parent and X's grandfather. These 4 cases are left case, right case, right case and right case. Let's understand all these 4 cases one by one. The first subcase is the left case where the parent P is the left child of grandparents X and X is the left child grandparent G and the X is the left child of parent P. So what we'll do over here is that we'll right rotate G and then we'll get this particular configuration and then we'll change the color of P and G. So P will be black now and G will be red now, and this will lead to the formation of a stable red black tree. So this is how we'll deal with a left case in Uncle Black. The second case is a right case, which is only a mirror of the left case we just understood. So now we'll consider left-right case where parent P is the left child of grandparent G and parent X is the right child of parent P. So what we'll do over here is initially we'll rotate the parent P to the left and it will lead us to this particular configuration. Still we are violating the conditions of red-black tree. So we'll now apply the left case where X is the new parent and P is the new X. Okay, so this is the left case, and then thus we'll right rotate G and then we'll change the color of X and G and we'll get this table configuration. So another case is Uncle Black and right case, which is a mirror of just right case we had seen earlier. So now let us begin with the deletion in a red black tree. To understand deletion, first we'll understand the concept of the term double black in the coming slides, and then we'll understand the concept of deletion. So we need to consider one thing in mind, that if we delete a black node, it is replaced by a black child. The black child is marked as double black. Okay, so this is the concept of double black. Now we need to convert this double black into a single black. So we'll perform normal standard BST deletion first, and then let V be the node to be deleted and U be the child that replaces V. Now even if U is null and when V is a leaf, color of null is still considered to be black, so U will still be considered. The first and the most simple case is that if either U or V is red, we mark the replaced child as red. So here we'll delete V and we'll replace it with U and we'll mark U as black, and this will balance our tree. Now here comes the concept of double black. So if both U and V are black, then what we'll do is that we'll delete V and we'll color U as double black. Now our task is to reduce this double black to a single black, and we'll see how it is done. So now here begins the subcase 2. We need to do this until the child node U will not be double black or it is not become the root. Okay, so the first subcase A will be that if sibling S is black and at least one of sibling children is red, we need to perform rotation. Now we'll denote red child of sibling S by R. Now the this can be further divided into 4 subcases, which are right case, left case, right case and left right case. Now we'll understand each of those cases one by one. So the first case that we are thinking about is the right case. We called it right case because the sibling S is the right child of the parent and R is the right child of S. So sibling S over here is right child of parent and the red node R will be the right child of S. So what we'll do over here is first we'll delete the node 20 and we'll make the node U double black, and then this will be the first case AI. What we'll do over here is that we'll left rotate the node 30 and change the color of node R to black, and this will provide us with a perfectly balanced tree. So this case is handled. Similarly, in the left case, left case is just a mirror of right case. So I think it does not need to be understood detailed. Now let's talk about the right left case. We call it the right left case because the sibling S is the right child of the parent P, while the node which is the left child, which is the red child of S, is also the left child of S. So we call it the right left case. So first what we'll do over here is that we'll delete the node 20 and replace it with the nil node U, which is the double black node, and we need to convert it to the single black. So this will lead us to the third subcase in the subcase A. Now what we'll do is that we will right rotate the node 35 over here, and it will lead us to this configuration after interchanging the colors of nodes 35 and 40. And then again we'll right rotate the node 30, and it will change the color of this node 40 to black, and it will lead with a balanced red black tree, which was what we required. So this is the right left case. Similarly, the left right case will be a mirror of the right left case, so it is not to be need not be understood in detail. Earlier we considered the case where the sibling was black and both of its children, either of its children must be red, but now what if both of the children are black? So this case handles when both of the children of the sibling are also black. So what we'll do is we'll perform the recoloring and recur the similar process for the parent if the parent is black. But if the parent is red, then we will just recolor and we don't need to recur for the parent, we'll just make our parent black. So we'll consider the case where the parent was black and we need to recur for the parent as well. So we can see over here this S is the sibling and both of its children are black. So after deletion, this will lead to the formation of a double black node U, and we need to convert this double black to a single black. So what we'll do over here is that we'll just recolor it, and we'll change the color of node S to black, and we'll make the parent node P as the double black node, and then we'll recur on the parent node phi, which is 20, to remove double black from that, and likewise we'll keep on moving upward and upward until we reach the root node and we get a balanced tree. So earlier all the cases that we considered, the sibling was black, but what if we get the sibling as red? So what we'll do is that we'll perform a rotation, we'll move the older sibling up, recolor the old sibling and parent, and this will again lead us to the cases which are discussed in 2A or 2B, where the sibling will again become black and either of its child will be red or both the child will be black. We have already known how to deal with these cases, but this case 2C will further be divided into two subcases, which is right case and left case, where left case will be a mirror of the right case. So we'll just look at the right case. So what is the right case? In case C is that the first thing is that the sibling will be red in color, which can be seen from here, and the right case is when S is the right child of its parent. So we can see over here that the sibling S is the right child of the parent. So what we'll do is that first we will left rotate the parent node, and it will recolor the parent node and the sibling node. Sibling node will be colored black again and parent node will be colored red, and then it will lead us to this configuration, which can be still seen as unstable. So now, but this particular case becomes the case 2B, where this is the U node and this becomes the sibling node. Now both the nodes of parent child nodes of this sibling are null nodes, which are black nodes. So it becomes the case where the sibling is black and both of its children are also black, and we have already known how to deal with this case in the case B. So we'll deal with this case, and finally the tree will be of this configuration, and then thus it is the balanced tree as it can be seen now. So what if the the node U becomes the root? Then we'll just make it single black node, and then we'll return, and this will reduce the height of the tree by 1. So now let's discuss about time complexity of insertion and deletion operation. Time complexity for both insertion and deletion operation on the red flag tree will be in O of log n in worst case as well. This is because of the balanced nature of the red flag tree. Okay, so now a question arises that why do we need to choose a red flag tree? So considering the case of BST, the average BST time for insertion, deletion or searching will be O of log n. But what if the worst case comes? The worst case is when the tree is either left skewed or right skewed. Then the time taken by BST will be O of h, where height of the BST it turns out to be the order of n. But what if we find some case, if we find some data structure where even in the worst case we can guarantee O of log n time? The particular data structure that we need will be satisfied by red flag tree, as it is a balanced tree, and thus the upper bound of the searching and insertion and deletion operation will also be O of log n always. Now, since AVL tree and red black tree are both self-balancing trees, let us discuss comparative analysis of both the trees and see how they differ. Okay, so with first property is balance. So there is no strict balance in red black tree in terms of height. It is achieved by coloring and recoloring of nodes. But in AVL tree, the height balanced AVL trees are height balanced trees, but maximum height difference between left and right subtree is 2. So there is more stricter balance in AVL tree as compared to red black tree. Now coming to storage, requires only one bit of storage to store color, but requires storage. AVL requires storage of integer part which stores the height difference for subtrees of a node for each node. Now, advantage of red black tree is faster insertion and deletions due to fewer number of rotations because of relaxed balancing, while the advantage of AVL tree is faster lookups and retrieval because of more strictly balanced structure. And the uses of red black trees in most of the language libraries like map, multiset, and so multimap in C++, while AVL tree is more used in database for faster retrievals. So now we'll end our discussion by discussing the applications of red black tree. Most of the self-balancing BST library functions like map and set in C++ are implemented using the red black tree. Then red black tree is also used to implement CPU scheduling in Linux, which completely fair scheduler, which is used by the completely fair scheduler. Besides, they are also used in k-mean clustering algorithms for reducing the time complexity. Moreover, SQL also uses the red black trees for indexing on the tables. Thank you. This was a brief introduction to red black